First proof is the sum for an arithmetic progression, and to prove this formula we write the arithmetic progression out. So a sum would be the first term plus the second term plus the third term right up to the last term. Now underneath that I'm going to write out the sum again, but I'm going to start at the last term, second last term, right up to the first term. And what we're going to do with both of these is add them together. So if I have sum of n and I add sum of n to it, I'm going to have 2 sum of n. I'm going to add the first and the last term, so a plus a gives me 2a, and we have this plus n minus 1 times d. And you can see that that's the same at the end, a plus a and the n minus 1 times d. So let's look at the second and the second last term. I have an a and an a, that's still going to give me 2a. I have n minus 2d, and I'm going to add 1 to that, so n minus 2 plus 1 is n minus 1 times d. And that's going to happen for every term that we add together. Now there are n terms in the sequence, so we know that multiplication is the shorthand way for repeated addition. So 2sn equals n upon 2a plus n minus 1 times d. So Sn equals n over 2 upon 2l plus n minus 1 times d. They could also ask you to prove this Sn equals n over 2 upon a plus l. You go through the proof for the previous up to Sn equals n over 2 upon 2a plus n minus 1 times d. And then we continue the proof. Instead of 2a, I'm going to write it as a plus n minus 1 times d. And what we have here is the last term. So remember, you've got to do all of the previous proof and then add these 3 lines. The sum of a geometric progression is given by the formula a upon 1 minus r to the power n all over 1 minus r. We start the proof in the same way that we started for an AP proof. The sum of the terms is the first plus the second plus the third right up to the last term. This time I'm not going to write them in reverse. What I'm going to do instead is multiply each term by r. So the first term times r is going to be ar. The second becomes ar squared. The third becomes ar cubed, right up to ar to the power n. And this time we're going to subtract. And if we look at this on the diagonal, we always have 2 terms the same. So when I subtract them, those terms are going to disappear. ar minus ar is 0, ar squared minus ar squared 0. There would be an ar cubed minus an ar cubed, ar to the power n minus 1 minus ar to the power n minus 1, all 0. So this gives us Sn minus r Sn equals a minus a r to the power n. Now I'm going to factorise both sides, and on the left we have a factor of Sn, and on the right we have a factor of a, and then divide, and we get our formula. The other formula that they could ask us to prove is that the sum to infinity is a over 1 minus r. And that starts by proving that the sum of n is a upon 1 minus r to the power n all over 1 minus r. So we use the previous proof. But what do we know here? We know that the modulus of r is less than 1. That means that if we have r to the power n, I'm going to show this on a graph, as n tends to infinity, r to the power n tends to 0. So the sum to infinity would be a upon 1 minus r to the power infinity all over 1 minus r. And what our graph shows us is that is a upon 1 minus 0 over 1 minus r, which gives us a over 1 minus r.